Okay, so from here we can see that the Q is actually wave vector K, and wave vector K also represent that this is in reciprocal lattice. Okay, reciprocal lattice. So you can see here that this is BZ. BZ stands for Brillouin zone. Okay, Brillouin zone. So from what we can see here, you can see like for this example, from 0, 0, 0 to half, half, half. Wait, okay, never mind. Okay, I'll show you this one. Okay, you can see that this is the structure for lead, and this is the structure for copper. And you can see that the shape is like this, right? From 0, 0, 0, 0, 0 is like this. So it is actually consistent with our experimental result. You can compare with our experimental result. For this is the experimental result, this one, and then this is our theoretical result. Yeah, same shape. Okay. So like just now I say that from 0, 0 to half, half, half. Sometimes we don't write the coordinate, but we write like L from 0 to L, from 0 to L. This point. So we write as half, half, half. So from our previous graph, we see that there exist the dispersion branches. For example, the FCC metals such as lead and copper. So I just want to show you two examples. One is for copper, one is for lead. So these branches are dependent on the direction of K, the wave vector, or sometimes we write it as Q. Okay. The center of the first Brillouin zone is at coordinate 0, 0, 0, and the data for the dispersion relation is obtained using the inelastic scattering of the slow neutron. Okay, so the experimental result that I showed just now was actually obtained using the inelastic scattering by the slow neutron. Okay, that's all for the linear monoatomic lattice. Remember, just now I said I will show you two models. The first model will be monoatomic, and then the second model will be diatomic. Okay, but it's still the linear. Linear means that it's only vibrate along x direction because we want to simplify it. Okay, so now, again, the atom vibrate in x direction, and then the wave function also along the x direction. Okay, but now the only difference is that previously there was a monoatomic, so there's only one type of the atom with the same mass. But now we have two different types of the atom with different masses. Okay, so we have the first type atom, we write it as small letter m, the black color one, with all with the same masses, the black color one. And the blue color one, all with the capital M, and then they have the larger mass. Okay, so now we have two types of atom with two types of masses. So the capital one is larger than the small one. That means that the capital, the blue atom is heavier than the black atom in this model. And the distance between two similar atoms is 2a. So from small m to capital N, A, and capital M to small n, the other A. So from small m to small m, similar atom is A plus A, 2A. Okay, so the lattice constant will be 2A, but the distance between atom and atom will be A. So we go through the same process. First, we want to know what is the displacement of atom 2R. Okay, this one. So displacement of this one will be U2R equal to AEI 2RK over minus omega t. Okay, this is exactly same with the monoatomic one, if you remember this one. This one, remember that? This one. But now because we are referring to atom 2R, so we just put 2R, 2R. And then same model. But previously we used the same type of the atom with same mass, but now we have two type of atom with different mass. But then the concept is similar. Okay, the concept is similar. So now we know that the small displacement of atom 2r will be the atom, the capital M, the 2r plus 1 equal to this equation. Why here we had A and here we had B? You have different amplitude because when you have different mass of the atom, definitely they will vibrate with different amplitude. So when you are referring to the lighter atom, then you have to use one amplitude, and here we use A. And you're referring to the second type of the atom. In here we use capital B to represent the amplitude of the heaviest atom. Okay, since the displacement for both types of the atom are small, then same thing, we use the Hooke's law to apply into the equation. Okay, similarly, we have F equal to MA. So F equal to M A. Okay, it is similar to the monoatomic. If you don't understand, you can review back the monoatomic model. Okay. Then this mu is the Hooke constant. Again, the same thing. Okay. So MA equal to KF. So from these two equations, we have two atoms. For the first atom is the lighter atom, small letter m, equal to this one. And the second atom is the heaviest atom, equal to this equation. Okay, so now we obtain two equations. One for light atom, small letter m, one with heaviest atoms, capital M. Okay, remember this one? This is what we use for the monoatomic model. Okay, so we have two equations. The first one is the equation that obtained from 9.8. This one and this one, these two equations, you apply into 2r plus 1. Okay, for 2r plus 1, you just apply here lah. Then 2r, you substitute into here. Okay, and then 2r minus 1, you just change it lah. Minus 1 minus, so just substitute to here. Then just solve equation 9.8. Then same thing apply to this equation. You apply 2r minus 1, 2r plus 1 into here. Then 2r, this one, into here, and then r minus 1 here. Okay. Okay, this is not, sorry, this is for monoatomic. Okay, when you see that in the slide, I have one dash box. All the dash box indicate the equation or the formula that we derived previously. But I want you to make the comparison, so I just put it here. Okay. So same thing apply to heavy atom here, and then we substitute 2r plus 2, 2r plus 1, and 2r here. So once you substitute everything in, then